Hey everybody, we are starting chapter 6. It's a pretty big chapter, so I'm going to split it up into 2 videos. Chapter 6 is on ionic and molecular compounds. So we're going to do some naming, we're going to talk about ions, we're going to talk about ionic and covalent bonds, shapes of molecules, all sorts of stuff. So if you are taking Chem 105 after this, if you're a nursing major, you're definitely going to want to pay attention to this chapter. And don't forget it, because when you start with 105, this information is going to be very important. So with that said, let's get started. Like I said, we're going to be talking about ionic and molecular compounds. And one of the biggest arenas where these compounds are important is obviously medicine. So, preparing and distributing pharmaceuticals is kind of a big deal. Let's talk about ions. So in this section, we're going to just work on writing the symbols for ions of the representative elements. Let's build some vocabulary first. We've got to talk about ionic bonds and covalent bonds. Ionic bonds occur when the valence electrons of a metal atom are transferred to the atom of a nonmetal. So remember, metals lose their electrons when they do chemistry. When they lose those electrons to a nonmetal, they form what's called an ionic bond. An example of this would be the bond between sodium and chlorine to make table salt. The sodium is the metal, and it loses its valence electron to chlorine, which is a nonmetal. Covalent bonds occur when nonmetal atoms share electrons and they achieve a noble gas arrangement. One example of that is carbon dioxide. The oxygen is not taking any electrons away from the carbon. They're just sharing electrons. So you'll definitely want to know the difference between these two. Here is kind of a depiction, and I'll put this line down the middle so that you can see we're talking about two different things here. So if you have a metal and a nonmetal, that metal is going to transfer its electrons so that it forms a positive ion, and the nonmetal forms a negative ion. That's an ionic bond. Whereas when you've got two nonmetals, you can see that they have incomplete octets, and we'll talk about octets in a minute. If they share an electron with each other, then they can both be happy. That's a covalent bond. You see, there's no negatives or positives there. They're just simply sharing electrons. Let's talk more about positive ions. So when you form an ionic bond, you've got a metal losing electrons and a nonmetal gaining electrons. With positive ions, we're talking about metals. So group 1A, group 2A, group 3A. If you remember, when we were talking about periodic trends, metals have a low ionization energy, which means that they give up valence electrons easily. So when they do that, they form an ion with a positive charge. The other trend that we talked about is the number of valence electrons that a metal has. So the group number is equal to the number of valence electrons. But that's only for the representative elements. So again, the 1A, 2A, and 3A. The groups that have an A behind them where there are metals. When metals lose their electrons, they have the same number of valence electrons as their nearest noble gas, which is typically 8 valence electrons. The exception being helium has 2. The term for a positively charged ion is called a cation, and it's named by its element name. So let's take our compound NaCl. The sodium only has 1 valence electron. When it loses it, it's Na+. The name of that ion is the sodium ion. Let's do a little bit more with this example so that you can see how all of this happens. Still working with our sodium, okay? So sodium is a group 1A metal. That means the cation it forms will have a 1+ charge because the group number is 1A. How do we get from the sodium atom to the sodium ion? Let's write the electron configuration for the sodium atom. This is going to be the abbreviated or condensed version. When you look at your periodic table, you're going to use neon, okay? Neon as your noble gas core. Then the only thing left is that valence electron in the 3s. When sodium loses that valence electron, it becomes the sodium ion. So that's how you name it. And the electron configuration is the nearest noble gas, which is neon. The 3s1, that's our valence electron. And we lose that when we form the sodium ion. Notice there's no 3s there. All metals go through this. They lose their valence electrons and they look like the nearest noble gas. So I did that kind of, live so that you can see the progression. This slide has all of that information, and it also talks about the number of protons and electrons, which I'll cover really quickly. But if you like to see things in words, nice, pretty, pre-made slides, I just included this in here so that you could see that. So one thing I didn't mention is that the sodium atom, the number of protons and electrons is the same. So the number of protons is 11. That's the atomic number. In the neutral atom, there are also 11 electrons. When you lose that valence electron, you now have fewer electrons than you do protons. And so that's where that charge of positive 1 comes from. Let's move on to negative ions. So negative ions are nonmetals, and they gain electrons. So the nonmetals that we're talking about are in 5A, 6A, and 7A. To figure out their charge, you're going to take the group number and subtract 8. And that will give you a negative number. Again, we're talking about representative elements here. And you want the number that has the A after it. So the 5, the 6, and the 7. Nonmetals, if you remember your trends, have high ionization energies. So you're not going to be removing any valence electrons from these. And instead, they will very happily gain electrons to form a negative charge. They'll gain electrons until they have the same number of valence electrons as their nearest noble gas, which is usually 8 valence electrons. A negatively charged ion, which we call an anion, is named by using the first syllable of its element name followed by ide, I-D-E. So let's talk about an example. We talked about the sodium part of table salt. Now let's talk about the chlorine part. Chlorine is in group 7A. So when we're talking about an ion that it forms, the charge is going to be 7 minus 8, which is equal to negative 1. The way we write that is the Cl with a negative sign. This means that it's going to gain 1 electron to complete its octet. Octet is just a fancy word for saying 8. So it completes its energy level with 8 electrons, so it's happy. The S and the P will be full. The electron configuration for the chlorine atom is 3s2. So we have the neon core, 3s2, 3p5. We've got 17 protons and 17 electrons. When it gains 1 electron, we're going to name it now. You take that first syllable, which is the chlor, and add IDE followed by the word ion. So it is the chloride ion. And I'll write the number in a different color. We've now got 3s2, 3p6. Well, that's a full octet. So instead of using a neon core, we're actually going to use argon. And argon is the noble gas that is in the same period as chlorine. And when you look at the number of protons and electrons, you've still got 17 protons. That's what makes a chlorine atom. Okay, that's what gives it its identity. But we now have 18 electrons, and that gives us the negative charge. Again, I have the pretty full slide here, okay? So if that's your jam, go for it. It has the same information. Here are some common ions and some formulas. So we've got the metals over here, which are the cations, and the nonmetals on the right. So this should help you when you're doing your homework and when you're studying for your exam. And again, this is a reminder about how you can use the group numbers to determine the charge for the ions. Now write it again. For cations, the charge is equal to the group number. And it has to be the one that has the A. For nonmetals, a little bit more work to figure those out. It's that group number that has the A after it, minus 8. So that's how you can figure out those ionic charges. Here are some important ions in the body. So salt is a big one, and it regulates and controls body fluids. You can get it from places like salt, cheese, pickles. Unfortunately, you can get it from processed food. A lot of fast food has a lot of salt. Salt is a great preservative, and it's a way to flavor a food very cheaply. So be careful if you like to partake in the processed foods. You don't want to have too much sodium. Then you have potassium, the potassium ion. It also helps regulate body fluids and lots of other cellular functions. You can get potassium from bananas, potatoes, orange juice, milk, lots of sources. The calcium ion, it is really important with maintaining bone health. So bones and muscle contractions, so pretty much your skeletal system. Milk, yogurt, so dairy, and then greens and spinach. Those are really good sources of calcium. You can also take a supplement, but it's always better to get it from the food. So don't just rely on the supplement. Magnesium is also really important. It's necessary for the bones, but it's also it's an ion that a lot of enzymes use to do chemistry. It also stabilizes your DNA and your RNA. Those are nucleic acids. So pretty much the blueprint of you being you is stabilized by magnesium ions. So very, very important, these ions. I'm going to go through this learning check for you. We have to write the formula of an ion that has 16 protons and 18 electrons. Before you can write the formula, you have to know what element you're talking about. And 16 protons tells us the atomic number. So you look at your periodic table and you'll find that sulfur has 16 protons. Now we're told that it's got 18 electrons. If we have 16 protons and 18 electrons, that means that we've got a negative ion, because we've got more electrons than we do protons. And the difference between these two is 2. So S2 minus is going to be the symbol for this ion. If we were to name it, let's just go there. We'd start with sulfur. That's the element name. We don't want anything after that first syllable. We replace all that with IDE and the word ion, so that the name would be the sulfide ion. Now let's say that we had an ion that had more protons than electrons. That's going to be a cation with a positive charge. So it would be a metal. Just like here, we've got a nonmetal. So use all the things you know to help you with solving a problem like this. Here's another learning check that we're going to walk through. And we're going to do a similar one in class. Let's talk about calcium. Identify the element as a metal or a nonmetal. Well, calcium is in group 2A. So it is an alkaline earth metal, which means it's a metal. The number of valence electrons, we look at the group number. There are 2. The number of electrons that must be lost or gained to acquire an octet. We're dealing with the metal here. So that means we're going to be losing electrons. And we have to lose 2 electrons to achieve that noble gas configuration. Now we've got to write the symbol, including the charge, and the name of the ion. So if calcium loses 2 electrons, then it's going to have a charge of 2+. To name it, we simply write the name of the element, which is calcium, followed by the word ion. Like I said, we're going to do practice like this in class so that you get the hang of it. Now that we've covered the ions, now we can put those ions together to form ionic compounds. Here are some properties of ionic compounds that you'll need to know. The first is that they consist of positive and negative ions. What keeps these ions together is an ionic bond, which we talked about in the last section. They have very high melting points, and they're solids at room temperature. So these are some properties of ionic compounds that you'll want to know. And sodium chloride, NaCl, is a great example of an ionic compound because it's something that you already know. You're going to combine sodium metal and chlorine gas, and you make table salt. Hopefully it's not spilled all over the table like it is in this picture. That's bad. And if you could look at the ions in a sodium chloride crystal, you'd see how they're arranged to where that sodium is donating its valence electron to chlorine, and chlorine's like, thank you, I will take that. So we keep mentioning things that look like this. This is a chemical formula. So NaCl, that table salt, that's the chemical formula. We use the symbols of the various elements and ions and subscripts to describe a compound. And you're always going to want the lowest whole number ratio of the atoms or ions in a chemical formula. When we start writing chemical formulas, I'll point out what that means. For an ionic compound, the sum of the ionic charges in the formula always equals 0. So the total positive charge has to equal the total negative charge. So with sodium chloride, you've got Na+, so that's a +1, and you got Cl-, that total charge is -1. So +1, -1, they cancel out, and the charge is 0. And then down at the bottom here, it's a visual depiction of this compound coming together. So sodium donating its electron to the chlorine atom, forming the sodium ion and the chlorine ion, and they're bonded together via an ionic bond. Here's another example. So this time we're looking at MgCl2. So magnesium is a group 2A metal, which means it's going to lose 2 electrons because it's got 2 valence electrons. If we're forming a compound with chlorine, chlorine can only accept 1 electron. So magnesium has to donate to more than 1 chlorine. So it's going to give 1 away to chlorine here and 1 here. So each chlorine atom gains 1 electron. When you look at the charges, the magnesium ion has a +2 charge. And then you've got chlorine, which forms the chloride ion. The charge on that ion is -1, but we have 2 chlorine atoms. So that means that our total negative charge is -2. So +2 from the magnesium, -2 from the chlorine, that means you've got an overall 0 charge. And what we formed is magnesium chloride. This is another example. So we're talking about how we can write these formulas and make sure that the total charge is 0. Let's say that we want to make a compound using sodium ions and sulfide ions. Well, sodium only has 1 electron to donate. That's not enough for sulfur. So we're going to have 2 sodiums to satisfy the sulfur. So we get a total charge of 0. If we only had 1, the sulfur would still be unhappy because it's still wanting 1 more electron. So that's why we have to do 2 sodiums so that it is 0. So let's write the formula for a compound with barium 2+ and chloride ions. If you're a visual person, This will help you. So that is the Lewis structure for the barium ion. Or excuse me, that's not the ion. That is the barium atom. We haven't made the ion yet. Then we've got the chlorine atom. And chlorine, again, is in group 7A. So it's going to have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Barium needs to donate 2 electrons. That means that we're going to need a second chlorine atom to take it on. Now what we have is our positive ion. I'm trying to do it here so that you can see the different colors. We've got our positive ion, the barium ion, and we've got 2 chloride ions that now are happy because they each have an octet. So the compound that you would form is BaCl2. And you can double check that by doing the total positives and the total negatives. The total positives here is +2. The total negatives, well, we've got 2 chloride ions, and they each have a charge of -1. And that gives us a total charge of 0. You don't have to draw all this out when you're figuring out the ionic formula, but if it helps you, do it. Now let's do some more with naming and writing ionic formulas. Before we can do that, we have to talk about the elephant in the room. We've been talking about groups 1A, 2A, and 3A, but there are a lot more metals than just those 3 groups. We've got all those transition metals in the D block. Transition metals form 2 or more positive ions, except for zinc, cadmium, and silver. So you'll need to know these exceptions. But by and large, if you have a transition metal, it's going to be able to form more than 1 positive ion. When we're writing a chemical formula or writing a name for a chemical formula, we have to be able to specify which ion is being used here. When we're writing the name, you're going to write the name of the element, and then you're going to put the charge as a Roman numeral in parentheses right after it. So no space or anything. Just put the charge right there in parentheses. This is what's called the stock system. There are other systems for naming transition metal ions. We're not going to talk about those. So here are some examples of transition metals and other metals in general that have more than one charge. So copper can be 2+, it can be 1+. So you're going to do copper 2 or copper 1. Iron 2+ or 3+. So again, you have to indicate that with the Roman numeral. And just so that we're clear with our Roman numerals, we've got examples here. But I'm going to give you Roman numerals up to 6. You shouldn't need all of these, but I want you to be prepared. So those are the Roman numerals from 1 to 6. If you need to, jot that down in your notebook so you don't forget. More often than not, you're going to be dealing with the charges of 2 and 3. When you're naming an ionic compound, you're always going to write the name of the metal, followed by the name of the nonmetal ion. When you're writing the name of the metal, you want to take into consideration whether or not you're dealing with a transition metal or not. So let's do a little practice. We have the ionic compound K2O. Your metal is always first. Like it is in naming, it's always first in the compound. Your nonmetal comes second. You look at your periodic table to figure out what element is K. That's potassium. Then you ask yourself, transition metal or no? If it's a transition metal, we have to include its charge. If it's not, we don't have to do anything more. In this case, potassium is in group 1A, so it is not a transition metal. So we simply have to write potassium as the first part of our name for this compound. The second part involves naming the nonmetal ion that is formed. You're going to start with the word oxygen because that's what O is. We keep the first syllable and get rid of everything else. Replace it with IDE so that the full name is potassium oxide. The crucial step that you don't want to miss is figuring out whether you have a transition metal or not. And if you do have a transition metal, is it an exception or is it a metal that will form multiple ions? Now let's say that you do have a transition metal and you're trying to name a compound. You can't name this compound without knowing the charge on the metal. So you have to use the charge on the anion and charge balance to calculate the charge on the metal ion. So last time we looked at the metal first and we were able to just name it straight up. Here, Mn, that's manganese. Transition metal or no? It's a transition metal, and it's not an exception. So that means we need to use a Roman numeral to indicate its charge. But we don't know its charge yet. So we've got to leave the manganese alone and go over to the anion. Here we have fluorine. That's what F is. And I'm about to write flower. Fluorine. Okay. So fluorine is a nonmetal, and it's in group 7A. Remember, you can figure out the charge of that fluorine really easily. You take the group number and subtract 8. So that's -1. The total negative charge, though, we have 2 of these ions. So our total negative charge is -2. That must mean that our total positive charge is equal to +2. We've only got one manganese ion here, so it has to have a charge of +2. Now we can write our name. You write the metal, followed immediately by the Roman numeral in parentheses. This tells us that what we have is manganese 2+. You take the first syllable of fluorine, that's the fluor, and add IDE. So this compound is manganese 2 fluoride. We're going to do plenty of practice in class, but you will need to do practice at home too. With naming, it's not difficult. There's just a lot of rules to remember. So you have to continually practice so those rules become ingrained in your brain. And even though it's not a math problem per se, you still need a method so that you don't forget any steps in naming. Because if you just went ahead and said, oh, it's manganese and fluorine, so that means that it's an ionic compound, and you write manganese fluoride, you would not be correct because you did not indicate the charge of the manganese. So if you forget the step of, is this a transition metal or not, you're going to get the answer wrong. So make sure you pay attention to detail. Let's name another compound. We've got FeCl2. The metal is always first, followed by the nonmetal. Fe, if you look at your periodic table, is iron. Transition metal or no? It's a transition metal. Is it an exception? No. The exceptions are zinc, cadmium, and silver. This is iron. Since it is a transition metal, we can't figure out its charge right away. We've got to go to the anion. Cl is chlorine. And just like its friend, fluorine, it's in 7A, group 7A. So the charge is going to be -1. That's what our ion looks like. We have 2 of these ions in the formula. So our total negative charge is 2 ions times the charge of -1, which is -2. That tells us that our total positive charge has to be +2. And there's only one iron ion in this formula. So it has to be a charge of 2 plus. Now we're ready to name. Take the element name iron, indicate the charge with the Roman numeral. You take the first syllable of chlorine, which is chlor, and add IDE, so that the full name is iron 2 chloride. Now let's say that instead we had where's my eraser? Something like this, where we've got a subscript on the metal. Sulfur is in group 6A. Its charge is going to be -2. So our total negative charge is -2. Our total positive charge is +2. But we've got 2 copper ions. So that means that our charge is going to be +1. And the name would be copper 1 sulfide. So that was a really quick example to show what you do if you have more than one metal. You take that total charge, the total positive charge, and divide it by the number of ions that you have. Here's a chart with metals and their variable charges. You've also got the names here too. I want to take a second to point out mercury, because mercury is kind of a funky little beast. So I'll blow it up here. Mercury 1 does not like to be alone. It likes the buddy system. So you actually have an ion pair, Hg2, 2 plus. So you've got 2 mercury 1 ions coming together to form an ion pair. You never see mercury 1 as just Hg plus. So keep that in mind if you are dealing with a compound that involves mercury. All the other ones are straightforward, but I wanted to point out mercury because it's a little bit of a funky example. This chart will be helpful for your homework. Likewise, this chart of names of some ionic compounds will be helpful because it gives you the pattern. Naming the metal ion, naming the nonmetal, and then putting them together. This last table here, the periodic table, it's got common ion charges. Now you will not have access to this for your exam. I apologize. But it will be helpful to you when you're doing your homework and you're doing the naming, so that you get familiar with the charges. And you can double check yourself when you're calculating the charge for a nonmetal or when you're figuring out the charge for a representative metal. So we took the chemical formula and wrote a name. Now we're going to take the name of an ionic compound and write the chemical formula. The first part of the name describes the metal. So it's going to give you potassium or iron 3. It's going to tell you what the metal is, and it may indicate charge if it's a transition metal. The second part of the name specifies the nonmetal ion. So you're going to have to take that root or the first syllable of that ion name and walk it backwards to the element. So let's do that. The iron 3 part is our metal. The chloride part is our nonmetal. Iron with the 3 in parentheses tells us what the charge is. So Fe3 plus is our cation. Chloride, that comes from chlorine. And I know we just did this, but I'm going to write it out anyway. It's group 7A. So its charge is going to be 7 minus 8, which is equal to -1. Oh. My brain and my hand are not connected. Okay. So our ion is going to be Cl minus. That's the chloride ion. Our charge on the cation is +3. Our charge on the anion is -1. Those two do not match. So we need to make sure that our total positive equals our total negative. Now, if we added another iron here, that would make the difference even bigger. So that means we've got to add more chlorine, add more chloride ions. If the charge for a chloride ion is -1 and we're trying to get to -3, we need to have 3 chloride ions. That way we would have +3 and -3. What that looks like is writing the subscript 3 after the Cl. One way that you'll see for how to do this is called the cross method. And I actually did the air quotes. You can't see my hands. I don't know. I guess it's just habit. So the cross method, you take the number for the charge of the cation and write it as the subscript for the anion. Now with chlorine, there is an implied 1 here, but we don't write the 1. So that's why you don't see a 1 after the iron. But if there was more than one, if we needed to have more than one iron, then we would write that in. So that's the cross method. And as long as you cross properly, you'll get the right answer every time. We're not done with ions. So we've been talking about what's called monoatomic anions, which means that you've got one atom that has a negative charge. But you can have groups of atoms that are covalently bonded and have an overall charge. That's what a polyatomic ion is. More often than not, you're going to have a nonmetal that is covalently bonded to oxygen. That's what a lot of the polyatomic ions are. Most of them are negative. So they have -1, -2, -3. The exception is NH4+, which is ammonium, and it has a positive charge. So it is the only cation that you're going to encounter that's a polyatomic ion. All the other ones are going to be anions. There's lots of products that are made with polyatomic ions. So they're actually really important. Hopefully no one has broken a bone, but if you have and you had a cast, the plaster cast is calcium sulfate. And this SO4, 2-, that's the sulfate ion. It's a polyatomic ion. If you like produce, which most people do, then you absolutely are going to appreciate fertilizer. And that consists of a compound that's got 2 different polyatomic ions. So ammonium nitrate is a component of fertilizer that helps plants grow. They need that nitrogen. This is a table that has the ions and their names and their formulas. You'll definitely be referencing this for your homework. Let's go through some of the names so that you can be more familiar with them. A lot of these common polyatomic ions end in ATE, sulfate, phosphate, nitrate. Some of them end in ITE, like sulfite, phosphite, and nitrite. The difference is that the ITE has 1 less oxygen than the ATE form. So SO4, 2-, SO3, 2-. Sulfate, sulfite. That's not how you spell that. Sometimes my brain. There we go. So 8 versus 8. We've got 4 oxygens over here and 3 oxygens for the 8. They have the same charge though. Same charge, just a difference in the number of oxygens. Some exceptions include cyanide and hydroxide. So they end in IDE, just like, doing sulfide or oxide or phosphide. If you take a polyatomic ion, a -1, and you add a hydrogen to it, you're going to add 1 to its charge. So if you have carbonate and you add a hydrogen, now it's HCO3-, whereas the carbonate ion has a charge of 2-. Another example is if you have sulfate and you add a hydrogen, you're going to go from the sulfate ion having a 2- charge to the bisulfate ion that has a -1 charge. So be on the lookout for that when you're doing your chemical formulas and writing names. Finally, halogens can form a lot of polyatomic ions. And each of them has a charge of -1. So if we start here with chlorate, it's got 3 oxygens. Chlorite has 2 oxygens. So that's something that we already know about, the ate versus the ite. If you have hypoite, then you're actually going to have even fewer oxygens. So if this is our gold standard, we've got 1 less oxygen and 2 less oxygens for our hypoite. You can also add more oxygen to get the per-ate form. So it's got 1 more oxygen. That's perchlorate. So it's the same thing with, say, bromine. You can have all of these different varieties. And it would be the perbromate, bromate, bromite, and hypobromite. So just be aware, there's always going to be 4 different polyatomic ions associated with each of the halogens. And when we say halogens, we mean fluorine, chlorine, iodine, and bromine. So I introduced those so that we can write formulas. When you're writing a formula from the name, you use the same rules of charge balance as you do for just the simple ionic compounds. The first word is always going to be your metal, and then your second word is going to be your polyatomic ion. I abbreviated that PAI because that's a lot to write. So magnesium, that corresponds to the magnesium ion, right? You have to look at your periodic table, figure out if it's a transition metal or not. It's not. So we look at the periodic table for the group number. It's in group 2A. So our magnesium, when it's an ion, it's Mg2+. Nitrate, you're going to look up on your chart. NO3- is nitrate. Our total positive charge would be +2. Total negative charge is -1. That's not quite right. The way that your book shows the charge balance, I'll do that for you here. And then I'll go back and do the cross method. So we've got our magnesium ion. We've got our nitrate ion. If we were to total that up in terms of charge, it would be +2 and -1. No good, because our charge, our overall charge, it's not 0. If we add another NO3- here, Now we've got +2 from the cation and -2 from the total charge of all the anions. So that means our formula is going to be magnesium, and then we're going to put nitrate in parentheses because we need 2 nitrates. So that's how you indicate multiple polyatomic ions. You put it in parentheses, and then you put the number as a subscript on the outside. So that's one way to do it. The other way would be to use the charge method, or excuse me, the cross method. You take the number in the charge for the magnesium, and that becomes the subscript for the anion. In this case, it is a polyatomic anion, so you have to again use those parentheses. There's an implied 1 here for the charge. We don't need to put a 1 for the magnesium, so we're just going to leave it alone. So you get to the same conclusion. Whichever way works best for you, if you need the visual of filling in how many nitrates you need, then use the first method. If the cross method is something that you did in high school chemistry and it just vibes with you, go for it. Either way, you'll get the same answer. Now let's do another one. We've got to write the formula for aluminum bicarbonate. The first thing we ask about that metal, transition metal or no? No. It is a group 3A metal, which means its charge is going to be 3+. Easy peasy. Now we've got our anion. That's bicarbonate. If you look it up on your chart, you'll see that's what it is. If you don't have your chart, you need to know that carbonate is CO3 2-. And when you add that bi in front, it means that you're adding a hydrogen. Let's look at our charge. So we've got +3 and -1. I'll show you both methods. Clearly not equal. If we added another bicarbonate, we still wouldn't be equal because now we've got 2-. But if we have 3 of them, then we'll be equal. So you write Al in parentheses, you write the formula for the ion, then you put the 3 on the outside of the parentheses. If you were doing the charge method, or I keep calling it the charge method, the cross method, you would take that 3 and drop it down as the subscript for the anion. And again, since there's an implied 1 in the charge for the bicarbonate ion, you don't have to write the 1 for the aluminum. But if it was anything other than 1, you would absolutely write it in there. Okay, one more example. These polyatomic ions can be a little tricky. Again, you're going to ask yourself, transition metal or nah? Sodium, nah. It's in group 1A. So your cation is going to be Na+, because group 1A tells you the charge. You recognize phosphate as a polyatomic ion. Oops. Getting ahead of myself. That is the phosphate ion, PO4 3-. Clearly, we've got to add some more something. The last two examples, we had to add more of the negative ion. But in this case, we actually have to add more of the cation, because -3, well, that's bigger than +1 in terms of the 3 versus the 1. So if we have 3 sodiums, then we'll have +3, which will balance out the phosphate. So the way you write that is Na3 PO4. Notice how there's no parentheses for the phosphate, because we're not doing anything to it. We don't have more than one phosphate. With the cross method, there's an implied 1 for the sodium. We don't need to write that here, but we do need to be concerned with that 3. So we get the same answer. So we wrote the formulas from the names. Now we've got to do the reverse. We've got to write the name from the formula, which is much easier than writing the formula from the name. You're always going to write the positive ion first, which is usually a metal, but it could be that ammonium ion. Then you write the name of the polyatomic ion second. And again, these compounds are still ionic compounds. We're talking about an anion and a cation coming together. When you recognize these different polyatomic ions, it helps you a lot with naming. And you just have to remember, you don't care about how many of each. You're just naming the different ions. So let's do a couple. CaNO3 The first thing we're going to do is name our metal. It's calcium. Then we're going to figure out whether or not we need to include the charge. Calcium is a group 2A metal. That means it's not a transition metal. So it's only got one ionic charge. That means we don't have to do anything else for that part of the name. The second word is going to be the name of the polyatomic ion. NO3 is nitrate. So it's calcium nitrate. Done. The second one, we know our first word is iron. That's the metal. But iron is a transition metal, and it's not one of our exceptions. So that means we're going to have to figure out the charge from the polyatomic ion. You look up PO4, and it's phosphate. It's got a -3 charge. In order for this compound to be, in order for it to have an overall neutral or zero charge, that iron needs to have a 3+ charge. So that's two examples of writing the name from the formula. Here's a table that's got some names and also some medicinal uses. So we've got an array of different medical uses, from antacids to antiperspirants, calcium supplements, all sorts of things. Epsom salt. I am familiar with Epsom salt. I am ashamed to admit it, but I've reached an age where Epsom salt is now in my home. I used to think that was just a grandma thing. It's not. So all of these are examples of ionic compounds that have polyatomic ions that are very useful. This is a flowchart for naming ionic compounds. As you'll notice, there's kind of an empty section over here. We're getting to it. So, this flowchart will be helpful when you're trying to name your different ions and for naming the compounds themselves. So use it, put it in your notebook. Almost done, y'all. We talked about ionic compounds, but now we have to talk about covalent compounds. These are molecular compounds. So a molecular compound forms when you've got nonmetals sharing electrons and forming covalent bonds. So we defined a covalent bond at the very beginning. The valence electrons are shared to achieve stability, whereas with the ionic compounds, we just had one donating to the other. And a molecule is just a discrete group of atoms in a definite proportion. So an example of that would be H2O. It's always two hydrogens and one water. Lord Jesus, my mouth is like, you've been talking too long. You can no longer speak coherently. 2 hydrogens, 1 oxygen. That is always what water is. It's the same proportion. If you change the number of hydrogens or the number of oxygens, you no longer have the same molecule. Naming is a little bit easier because we're not looking at charges or anything like that. What we're looking at is what element is it and how many of them are there. So let's use our water example to name a molecular compound. The first nonmetal is in the formula is just named by the element name. So in ours, that's hydrogen. But we've got more than one hydrogen. That means that we have to use a prefix. The number of hydrogens that we have is 2. And you'll notice this chart that has the prefixes for naming molecular compounds. If there are two, then we use di. So our first part is dihydrogen. Then you name the second nonmetal, kind of like we were naming the anions. You take the first syllable. In our case, we've got oxygen, so that's ox, followed by IDE. There's no subscript there, so we don't need to add anything. So the name, the molecular name, is dihydrogen monoxide. So if there's one of the second element, you've got to include that. I almost got tripped up on it. There's a lot of rules, man. So with these molecular compounds, you can have the same two elements, but form multiple different compounds. So if you've got CO2, you name the first, that's carbon. Then you name the second and include information about how many there are, right? Di means two. Oxygen, so we're going to use ox, followed by IDE. But if you only have one oxygen, it's carbon monoxide. So the number of oxygens matters, and you can see the difference in the name just by the prefix that's used with the oxygen. And when you have two vowels together, like O and O or A and O, you omit the first one. So usually that comes up when you're doing monoxide or pentoxide. You name the first element, nitrogen. We've got mono because there's one oxygen. But you don't write monooxide, okay? That OO, no. OO is no. So it's nitrogen monoxide. The other example would be if you had something like this. For the oxygen part, 5 is penta, but we don't write pentaoxide. You get rid of the A for pentoxide. Here are some common molecular compounds, things that you may recognize. So carbon dioxide, everyone recognizes. You may also recognize dinitrogen oxide, that's laughing gas. So if you have a terrible fear of like the dentist or something like that, they may give you some laughing gas to take the edge off. Sulfur dioxide is something you may not know that you're familiar with, but if you like trail mix or like dried fruits, sulfur dioxide may be one of the components that's used to preserve that fruit. I personally don't like the taste. So when it comes to like banana chips and dried pineapple and stuff like that, it's not for me because I can taste that preservative. I'm not a fan. But if you are, go for it. Have my portion. Let's do some more practice with naming. So we've got NCl3. You name the first, and that's nitrogen. Then for the second word, you're going to look at, okay, do I have a subscript? Yes, I do. That chart, when I first introduced this, will tell you the prefix that you need to use. So tri is for 3. You're going to take the first syllable of chlorine, that's chlor, and write IDE. So it's nitrogen trichloride. One more example. Now we see, we've got a subscript for our first element. So we have to use di to describe how many we have. B is boron, which we don't do enough with. The second word, we're going to start that with our prefix, tri, because there are 3. Followed by oxide. Notice how here we don't have to take out one of the vowels. So it's only the OO or the AO, those really awkward ones. But trioxide is perfectly fine. So diboron trioxide would be the name. Now we have to go in the reverse. If you have the name, you need to be able to write out the formula for the molecular compound. You're going to be given the name with the 2 nonmetals and then prefixes if you need to write a prefix to show the subscript. So an example would be diphosphorus pentoxide. Diphosphorus, well, phosphorus is P. Di means 2, so we're going to put a subscript of 2. Pentoxide, this little tiny part, ox, tells us oxygen. So we write our O. Pent is very close to penta, and that prefix means 5. So P2O5 is the formula for this molecular compound. So we've talked about ionic compounds and covalent compounds and the differences between them with naming, writing formulas, etc. To identify whether or not a compound is ionic or covalent, look at that first element. If the first element is a metal or it's that NH4 plus, you're looking at an ionic compound by and large. If the first element is a nonmetal, then you're looking at a covalent compound. So make sure that you can tell the difference between the two. Just shorten it up. Ionic, you've got metal or NH4 plus first. Covalent, nonmetal. So you don't see any metals in a covalent compound. As promised, here's the other part of that naming flow chart. So you've got the ionic compounds and the molecular compounds, which have the covalent bonds, and all the rules for how to name them. So use this flow chart when you're doing your homework and practicing, because it will help you get the rules and get the flow of how to name compounds. So here's a learning check. I think you should try to pause and do it. So this is, you can take the time to identify each compound as ionic or molecular. Just judging by all the names, you can see what type of compounds these are. But pause it and try it. And then you can also do, choose which one is the right name. So I'll do these answers for you now. So all of these compounds are molecular. The first element, they're all nonmetals. And silicon is kind of a semi-metal, so it's kind of in between. But you still use the naming for the molecular compounds. So we've got 1 silicon and 4 chlorides. That's C. That tetra tells you 4 chlorides. P2O5, we just did that one. But you're looking for the one that's got something for the 2 and something for the 5. And the only one that's got that is C, diphosphorus, so that's 2 phosphorus. Pentoxide means 5 oxygens. And then Cl2O7, you need something that's got dichlorine because there's 2 of them. And then there's 7 oxygens. So heptoxide. That one's going to be A. So make sure that you're paying attention because these naming ones can be tricky. So this is it for the first video. I'll give you your reminders. First reminder is there's a part 2. So you should watch that. Naming and writing chemical formulas, that was the bulk of the first part. Now we're going to do a little bit more deep diving in the second part to talk about the writing Lewis structures and naming the different shapes and looking at bond angles of these ionic compounds and these molecular compounds. So you need to watch part 2 as well. Your exam 2 covers chapters 4 through 6, and it's going to be available Wednesday, October 7th. It will be available until 11:59 p.m. Eastern Time on October 9th. I will put the periodic table and all other acceptable things that you can use for exam 2 in a folder called exam 2 in course content, exactly the same way that I did for exam 1. You print those things out before you take the exam. You can use a scientific calculator, not your cell phone. And you can have some scratch paper too for, jotting down notes or figuring out problems. You will not be required to upload your work this time because we're not really doing heavy math like that. You also have Chapter 6 Mastering Chemistry homework and quiz, and that's due on October 11th. There's no chapter check-in this week. You've got an exam to study for, and you've got Mastering Chemistry. Do the Mastering Chemistry homework and quiz as a way of helping you study for the exam. So with that, again, watch part 2 because you'll need it. And we'll do some practice in class along with a little bit of review. So I'll see you in class on Tuesday.